This is Colin Selleck of Binghamton University. This video lecture is for the course ME273 Statics, and we use the book Statics by R.C. Hibbeler. Today I'm going to cover Chapter 8.1, Characteristics of Dry Friction, and 8.2, Problems Involving Dry Friction. After today, you will be able to understand dry friction, and you'll be able to draw a free body diagram that includes friction and to solve problems that involve friction. First, we'll look at some applications. I'll give you some characteristics of dry friction, then we'll go over some problems involving dry friction, and then we'll do some problem solving. But first, some applications. In designing a brake system for a bicycle, a car, or any other vehicle, it's important to understand the frictional forces involved. For instance, for an applied force on the brake pads of this bicycle, how can we determine the magnitude and direction of the resulting frictional force? And that frictional force is what's used to slow down or stop the bike or the vehicle. Here we see a man using a rope to tow a refrigerator. In order to move the refrigerator, is it best to pull up as shown at this angle? Is it better to pull horizontally or pull downwards on the rope? We're going to investigate this in greater detail when we look at sliding versus tipping. So let's talk about dry friction. Friction is defined as a force of resistance acting on a body which prevents or resists the slipping of the body relative to the second body. Experiments have shown that the frictional forces act tangent or parallel to the contacting surface in a direction opposing the relative motion or tendency for motion. So let's take a look here. We have a block resting on the ground. We have an applied force P, and we of course have the weight of the block. Now if we look at what's going on here, the surface is kind of rough a little bit. You can imagine, think about sandpaper or something like that, but even smooth surfaces have microscopic defects in them, and you can see that here. This gray stuff is the ground, and it has these irregularities in it, as you see here, as does the block. The block also has irregularities in it as well. So what is going to happen is that we're going to have contact points that are going to be changing over time, and at each contact force, at each contact point rather, there's going to be this resultant force that you see here, and it's normal to the surface of the points of contact right there. And that normal force can also be resolved into its two x and y components. The y component we call the normal, and the x component we call the frictional force. So if you sum all these up together, it sort of looks like this free body diagram here. Now we have all these little delta n's here, and all these delta frictional forces here. And we can resolve those into one resultant force, as you see here. Now we have the normal force, which acts at some distance x away from the center of the block. And we have the frictional force, which is acting opposing the direction of the impending motion. So if we're pulling on it, motion is going to probably be in that direction, or it is going to be in that direction. So the frictional force is opposite that. Now for this body right here to be in equilibrium, we know that just from summation of forces in x and y is that P is equal to F, right? And N is equal to W. If we sum moments about point O right here, we have the weight, right? It wants to rotate counterclockwise. It's positive. It's x distance away, so it's x times W. And the frictional force and normal force pass through O, so there's no moment due to that. Now the moment due to P, it wants to rotate clockwise, so it's negative, and it's a distance h away from O. So that would mean that x times W equals h times p for this block to be in equilibrium. Now to study the characteristics of frictional forces, let's assume that tipping does not occur. Okay, so the block's not going to tip over, so that means that h is small or a is large, right? So we're assuming that first of all, the block is not going to tip over. Then as you gradually increase this force P, and you can see it in this curve right here, the frictional force starts to grow, right? This is the frictional force on the y-axis. This is P on the x-axis. So as P starts to grow, so does the frictional force, right? And then at some point, all of a sudden, motion is going to start to occur. And when that happens, as we'll see soon, the frictional force gets reduced. Now, experiments have shown that the relationship between F and P is as shown at this 45-degree angle here. Now, the maximum frictional force attained just before the block begins to move, and we call that impending motion. So the maximum frictional force is attained just before the block begins to move, and we call that impending motion, and that happens right here. The value of the force at that point is defined by F sub s is equal to the mu sub s times the normal force, and mu sub s we call the coefficient of static friction. And the value of mu sub s depends upon the materials involved, and you can go to books and look that up. You know, steel sliding on copper, aluminum sliding on aluminum even. So mu sub s has been characterized for many different types of materials. Now, once the block begins to move, the frictional force tends to drop, as you can see here. And when it does that, the frictional force now is F sub k. That's the kinetic. Kinetic means I'm moving. So the kinetic frictional force is equal to mu sub k times n, where mu sub k is called the coefficient of kinetic friction. Now, we won't be using this equation in this class, but in dynamics we will be using that equation. So just before the block begins to slip, we can calculate the frictional force as mu sub s times n. Any time before it slips, we cannot use this equation, right? Because we're down in here somewhere. It's only at the point of impending motion that we can use this equation right here. Now let's look at the free body diagram of impending motion. Here's that resultant force we talked about earlier, and it's broken into its two components, F sub s and the normal force. And the normal force is said to be acting at some distance x away from the center line of the block. Again, it's very important to note that the friction force may be less than the maximum frictional force. So don't just assume that the frictional force is equal to mu sub s times n. That's only true, as I said earlier, at this point where it's impending motion. Now, we can talk a little bit about how they determine the coefficient of static friction experimentally. Here's the free body diagram. So we're assuming impending motion in this case. So that means that the frictional force is going to be equal to mu sub s times n. And n is said to be acting at some distance x away from the center line of the block. The frictional force is acting opposite the direction of impending motion. And we see we have the applied force P and the weight. So if you look at this right here, there's this angle phi sub s. And by looking at that, you know that the tangent of phi sub s is equal to, well, it's this right here, which is F sub s, divided by this, which is n. And since F sub s is equal to, this is impending motion, you know, so F sub s is equal to mu sub s times n, the n's cancel out, and we get the tangent of phi sub s is equal to mu sub s. And the way this is realized in experiments is shown here. What we do is we put a block on top of a plane right here that can be tilted. So initially it starts off when phi sub s is equal to 0. And then as the block is lifted, the point at which it just begins to slide is noted, and that angle theta sub s is measured. And from the previous page we got that. I know they use phi on the previous page, it's kind of confusing, but the tangent of that angle is going to be equal to mu sub s. Now let's go over some steps for solving problems involving dry friction. Now we're in section 8.2. So draw the free body diagrams, making sure that you show the frictional force in the proper direction. It always opposes the motion or the tendency for motion. Determine the number of unknowns. Again, don't assume that F is equal to mu sub S times N unless you're in impending motion. And then we apply the equations of equilibrium and the appropriate friction equations to solve for the unknowns. Now let's talk about impending tipping versus impending motion. So here we have a man pushing on this box. And the question is, will the box slide or will it tip over about that point right there? If we draw the free body diagram of this box, we have the force the man's pushing with, P, we have the weight of the box, we have the frictional force, which is in the opposite direction of impending motion, so it's to the left, and we have the normal force acting at some distance x away from the center line. So we have four unknowns. We have W, F, N, and X. So we don't have enough equations to solve that. Because at most in 2D we can solve only three for three unknowns. So we have to make some sort of assumption to give us another equation, and that equation is going to be the friction equation. And then we can solve for those unknowns, but then we have to go back and check to make sure that our initial assumption about friction was correct. So here's how you do it. First, you can do these problems in one of two ways. First, you can assume that impending motion is about to happen, and then we know that the frictional force is equal to mu sub S times N. So now we can solve for the unknowns X, P, and N. Now, if X is greater than B over 2, right, that means that the normal force is off the body. That means that your initial assumption was incorrect. So you use this right here to determine if your original assumption about friction was correct. So if X comes out to be greater than B over 2, you know that you made the wrong assumption, and you have to go back and then assume impending tipping. And in that case, we know X. Because in impending tipping, we're about to tip about this point, so all the normal force is concentrated right there. And it's a distance x away. So we know x in this case is b over 2. So now we can solve for p, n, and f. And then you have to go back and check. Make sure that f came out to be less than mu sub s times n. If you did impending tipping first instead of impending motion, you would go through this process. Assume x is b over 2 and solve for the three unknowns. And then check to see if f is less than or equal to mu sub s times n. If it's not, then your initial assumption was wrong and impending motion is the case. So let's go over an example to make this clearer. We have this crate, it weighs 250 pounds. The coefficient of static friction is 0.4. Find the maximum force P that can be applied without causing movement of the crate. So this problem is exactly this problem right here. So let's see what happens. So what's our plan? We're going to draw a free body diagram of the box. We're going to make some sort of assumption about friction. So you either assume it's about to move or you assume it's about to tip. And then you apply the equations of equilibrium and your friction equation. And then you always go back and check to make sure your initial assumption about the friction or your initial assumption about is it going to tip or is it going to slide is correct. Okay, here's the free body diagram. The crate, we're asked to solve for P. It's an unknown. Here's the weight, 250. We have the known dimensions. We have the frictional force, and we have the normal force acting at some distance x away from the center line of the box. So I'm going to assume that the crate is about to slip. So that means impending motion. So that means that F, the frictional force, is equal to mu sub s times n. Mu sub s was given as 0.4. So my assumption is impending motion. So again, we're assuming impending motion, so F, remember, is 0.4 times n. And establish a coordinate frame, and some forces in the x direction is equal to 0. We have P in the positive direction minus F in the negative direction, so minus 0.4 times n. And summing forces in the y direction, it's equal to 0. And we have the normal force minus the weight is equal to 0. Solving those two equations, you get that N is equal to 250 pounds and P is equal to 100 pounds. So now the next step is to sum moments about the point O. So some moments about O. The weight passes through O. P is 4.5 feet up. It wants to rotate clockwise, so it's negative. Summation of moments is 0, so this will be minus 4.5 times P. F passes through O, so there's no moment due to that. And N wants to rotate counterclockwise, so it's positive, and it's x distance away, so plus x times N. And when you solve this equation, you know P is 100 pounds, so and N is 250 pounds. So x comes out to be 1.8 feet. Now, we have to go back and check our assumption. Is x greater than half the width of the box? Half the width is 1.5. So x is greater than half the width of the box. So our initial assumption was incorrect. So therefore, tipping is going to occur. So now we have to go back and start over, but this time we're going to assume, or now we know that tipping is going to occur. So now we have this free body diagram. The normal force is now moved to the very edge of the box because we're about to rotate about that point right there, so all the normal force is concentrated there. And again, we'll just establish a coordinate system. Some forces in the x direction is equal to 0. We have positive P minus F. And summing forces in the y direction equal to 0. We have N minus 250. So the last thing to do is to sum moments about O. So we sum moments about O, and we get, so P wants to rotate clockwise about O, it's 4.5 feet away, it's negative 4.5 times P. The normal force from this equation right here is equal to 250 pounds. So it is 1.5 feet away from O. It wants to rotate counterclockwise, so it's positive, so plus 1.5 times 250. Now this is the normal force there. And when you solve all these equations, you get P is equal to 83.3 pounds, and F is also equal to 83.3 pounds. So let's do another one. Here we have an automobile. Has a mass of 2,000 kilograms, and mu sub s is equal to 0.3. And it's being pulled by this rope at an angle of 30 degrees. Find the smallest magnitude of F required to move the car. Now, we're going to assume the back brakes lock and the front wheels are free to roll. So first we're going to draw a free body diagram, take a look at our knowns, and then make some sort of assumption about friction. Is it about to slip? Is it impending motion, or is it not? And make sure you go back and check your assumption when you're done. Alright, so here's a free body diagram of the car. We'll establish our coordinate system. We have the weight of the car, and that is the mass times acceleration due to gravity, and this is equal to 19,620 newtons. And it operates at the center of gravity of the car, which was, we know the dimensions. We have the force in the rope acting at 30 degrees. Now the front wheels are free to roll, so there's no force in the x direction at A. But there is a normal force at A. Likewise, there's a normal force at B, but the rear's wheels are locked. So therefore, we're going to have a frictional force on the rear wheels. So let's just sum forces in the x, and that's equal to 0. So we have F sub b minus the component of F in the x direction. It's negative, so minus F times cosine of 30. Sum forces in the y direction, it's equal to 0. We have the two normal forces, and we have the component of the force F in the y direction. So it's positive, so plus F times sine of 30. And then we have the weight of the car, and it's negative, minus 19,620. And lastly, we'll sum moments about point A. Set that equal to 0. So first let's take a look at F. It's got two components, right? There's F sub y, which is equal to F sine of 30, and there's F sub x, which is equal to F cosine of 30, and both of those have a moment about A. So let's do the x component first. So it's F sub x is F times cosine of 30, and it is 0.3 meters up from A. It wants to rotate counterclockwise, so it's positive, so this would be times 0.3. Now let's look at F sub y. F sub y wants to rotate clockwise about A, so it's negative, so it's minus F sub y, which is F sine of 30, times its distance away from A, which is 0.75 meters. And now we have the weight, right? It wants to rotate clockwise, so it's negative, so minus 19,620. And the weight, the center of gravity is 1 meter away, so it's times 1. And lastly, we have N sub b. It wants to rotate counterclockwise about A, so it's positive, so plus N sub b. And its distance from A is 1.5 plus 1, or 2.5. Now, if we assume the rear wheels are about to slip, we can assume that F sub b is equal to mu sub s times N sub b. And we were given mu sub s was 0.3. Now we're assuming it's about to slip because we were asked for the maximum force required to move the car. So we're in the impending motion condition, so therefore we can use this equation. So now we have four equations, four unknowns. I'll leave it to you to solve those. The answer is F comes out to be 2762 newtons. You know, on a test or something, you really should say 2760, three significant figures. N sub A comes out to be 10263. So on a test, you would tell me 10300. N sub B comes out to be 7975. These are all newtons, by the way. And on a test, you would tell me what, 7980. And lastly, F sub B comes out to be 2393 newtons. So on a test, you would say 2390. Okay, that concludes characteristics of dry friction 8.1 and 8.2, problems involving dry friction. The next video is on wedges. We are not going to cover 8.4, frictional forces on screws, and but we will go over frictional forces on flat belts. See you in cyberspace.